Hello everyone, welcome to the tutorial 6. I quickly made a video for students on Monday morning section because I prepared the wrong version of the tutorial 6. And now let's take a look. I highly recommend students to review the catch part since it's very important. And if you want to find some external resources, here's one recommendation. Scan the QR code and take a look. So on the right hand side, you can see this is all the video numbers. So check out these videos. And let's go to the question 1. So question 1 is about CPU cache design, about the eviction policy uh, uh, question. So if a cache that we had use the least recent used policy, that is a new data block replace the cache block that has been unused the longest. And we need to meet these two design criteria. The first one, design an arbitrary long sequence of access that use as a few memory blocks as possible and still result in every access being a cache miss. And you can test the sequence. You can test your sequence up above in the simulator by using this code. So basically, just accessing the position 0 and then 1, 2, 3 until n. And when we access the 1 again and 2, it's still a cache miss. How we design cache that can create cache miss for each time of accessing the memory block. And another question is if the cache used furthest in future policy, that is replacing the cache blocks that will be used furthest in the future instead of least recent use, what the proportion of access would be cache misses. Would such a policy be practical in a real CPU? Pause the video and think about this question. And after 5 minutes, if you figure it out, you can check out my explanation part. Okay, so this is an answer of question 1. The sequence we want to access to the n+1 block in a round-robin fashion. So basically, we have fully associative cache, and we have n data points. So what do we want? We want this memory has n+1 block, and it's in a round-robin fashion. So when we checking the data 1, when we're checking the 1, it's a cache miss. So the first n time is a cold cache miss. And because we have n+1, and the n+1, when we access 1, is still a cache miss. And when we go to the 2 will access the previous 1 block, and 3 will access the previous 2 block. Then it's still a cache miss. So each of time is a cache miss, and it's always a cache miss. So this is how we design this one. So that is the program access block 1, 2, 3 until n-1 and n+1. And then back to 1, 2, 3, n-1, and n+1. So in the end, it will all be a cache miss in this way. So with the furthest in future algorithm, we start with a sequence of n code misses. After that, when accessing n+1, we replace n. Accessing block 1 through n-1 will cause cache hits. Then the access to block n will replace n-1. Following this pattern, we see that we get 1 miss every n access. Note that for this particular access pattern, the MRU most recent use algorithm provides exactly the result we want. Though this algorithm is not very efficient for those type of patterns. So this is the answers of question 1. And now let's check out the question 2. So question 2, we have 3 questions inside question 2. Consider a computer will, first condition, the memory is byte addressable. 2 condition, second condition, memory access are 1 byte word, and address are 13-bit wide. The cache is directly mapped with 8 byte block size, b equal to 8, and 4 sets, s equal to 4. And here's the context of the cache. And the first question they ask you to fill in this 13 bytes of this information here. So basically, we need to list out which bits representing the block offset, which bits representing the catch set index, and which bits are for the catch tag. And the question B, we need to when you answer, list all of the hexadecimal memory addresses whose contents would be stored in set 2. And in question C, we need to answer what would be the content of the cache become if a program were to access the following memory address. We got the following memory address, and we need to access. So after each of the memory search, what is the result? What would be the result of the content of the cache? And pause the video for 5 to 10 minutes, think about it, and once you figure out, compare your solution with mine. Okay, let's check out the solution of question 2. So consider a computer, like we have 4 conditions for these questions, and it's very important. First of all, the cache is direct mapped, which means is also one-way associative. So the associativity equal to 1 in this case. And we have 8 byte block size. That means 8 bytes 2 power of 3, right? And we have 4 sets, and 4 is 2 power of 2, right? Remember, in cache, we always have 3 components for the cache labeling. The first part is tag, and second followed by the index, and then followed by the offset. The offset, the digits of offset controlled by the block size, and the digits of the index controlled by the number of sets. By direct mapping, it means it's one-way associative. Just to mention about that, and since we know the block size is equal to 8, so that's 2 power of 3. So that means we need at least 3 bits to distinguish the 8 byte block size, to distinguish the block size when it's equal to 8 byte. So that's so the offset, we have 3 bits. And for the index, because we have 4 sets, to distinguish each of the set, we need 2 bits to distinguish 0, 1, 2, 3, 4 with 0, 1, 2, 3. So we have 2 bits for the index. And by using the C0 representing the catch block offset, we get the C0, we have 3 C0 and 2 CI, and then the rest all tags, then the rest all the CT, all the tags. So back to the question 2. The question 2 was asking, question 2 was asking, list of all the hexadecimal memory address, whose contents would be stored in set 2. And every address of the form with, I think the most important 2 digits for the set number, when 0, 1, where can be either 0, then the rest, like the index number has to be 1 and 0, then the rest can be either 0 or 1, will hit in set 2. Because when representing the 2, it's just a 1, 0, right? So the only thing matters are the digits 4 and digit 3 in the position. So only these 2 matters. The rest all doesn't matter. Either 0 could be either 0 or 1. And if you're writing in hexadecimal, these are addresses of the form WXYZ. So well, W is either 0, 1, X can be anything from 0 to F. Y is one of the 1, 3, 5, 7, 9, B, D, F, and Z. And it can be anything from 0 to 7. So Z can be anything from 0 to 7. So this is a question 2, part A and part B. Let's check out the part C. Part C is slightly harder. So we first need to, because we have the following 4 memory address we need to access. So by using the previous tag information and index and offset, how many digits we need to use, this information, we can turn that information into this table. And this is the original content of the cache. And for the first one, For the first one, index is equal to 1, offset 2. So we need to check the set index 1. And the catch set 1 contains a valid entry, so it's a valid for the catch 1, for the set index 1, but its tag is not EB. Check the tag is 45 in this case, but what we want is EB. And hence, we fetch the data from memory and store it into catch set 1. So we're replacing this the set index 1 with a new data that we retrieved from the memory. And the second one, by the way, this is the second one we want to access. It's the index is 0, so we go check the set index 0, and also it's valid, and the tag number is 09. So okay, we have the information here, and the offset is 5. So we are checking the set index 0, valid tag 09, and the byte information 5. So we got the return value should be 3F, and the catch remains unchanged. And let's move on to the third memory address. And the third memory address, the index is 3, so we need to go to the set index 3, and the tag number is 06. Okay, confirmed. We have tag 06, but it's invalid. So what we should do? The valid base is 0. Hence, we fetch the data from memory and store it into the catch set 3, replacing the data that is already there. Because it's invalid, this block, maybe they are doing some operation here. So at least for this moment, we cannot read the memory. So we have to dump everything inside the set index 3 and fetch the new one from the memory. And then here we got, this is a new memory, this is new data. And then the last memory address is still the set information 3 and tag 06. Okay, confirm, we got 06, and right now it's valid because the previous one we fetched the new data and it's valid. And the offset 7, so we need this data, so it's DF, and the catch remains unchanged. So this is how we read the data from the catch memory. We need to first check out the corresponding set index to check the valid information and check the tag. If they both okay, information is valid, and also we have this tag number, then we can continue. We can perform reading. But if any of the above information does not match, then we have to retrieve the data from the memory. So basically, dump everything in the cache, and then loading the information. So that is the end of question 2. And let's check out the question 3. So question 3, very similar to question 2, but in this question, the catch is a two-way set associative, so E equal to 2, with 4-byte block size, B equal to 4, and 8 size, so S equal to 8. And you can see from here we have two line number 0, line number 1. That means they are two-way set associative, and each of them, like for each set, we have two lines. So very similar to question 2. First of all, let's fill out this information table. And question B is a list of all the hexadecimal memory address whose contents would be stored in set 2. And then the question C would be what would be the contents of the cache become if a program were to access the following memory locations in this order. So assume that the cache used the least recent use replacement policy, and that for memory location not already present in cache, the same rules as the previous question apply. So similar to the previous question, but we change it to the two-way set associative cache. And pause the video, think about it for 10 minutes. Once you got it or you're still struggling with it, check the solution. Okay, let's check the solution. We have the information at the beginning. So the cache is a two-way set associative, E equal to 2, with 4-byte block size, B equal to 4, and 8 sets, S equal to 8. So we have 8 sites. That means the number of the index should be at least three bits. And for the offset, it should be at least 2 bits because the offset will basically determine which block you are referring to, and the index are referring to which set you are talking about. So in this case, in this question, we only need 2 for the block offset, and we need 3 bits for the catch set index, and then the rest all the catch tag. And this is question A. For the question B, very similar to previous one. Since we need to know everything in set 2, so the only bits matters are the bits 4, 3, and 2. So this 3 should be 0, 1, 0. Then the rest could be either 0 or 1. Will hit in set 2. So writing in hexadecimal, those are address of the form 008 to 00B, 0028 to all these numbers, and so on. So where the initial ZZ can be replaced by any value from ZZ to 1F. So highlight, only thing matters in this case are the bits sequence 4, 3, and 2. So this 3 should be 0, 1, 0 because that represents for 2 in binary. And question C is a bit longer, so let's we spend some time to take a look. First of all, we need to divide the bits of the memory address that they provided us into a readable content, right? Into a tag, index, and offset format. So we can using this table to check out the original memory table. And the first one, index is 2, so we are going to the set index 2, and the tag is EB. Okay, tag EB confirmed, but we got 1 is invalid. So what we should do? The catch set 2 already contains an entry with tag EB, but it is not valid, and hence we fetched data from memory and stored it into catch set 2. So you can check for this case, we loaded the new data from memory for the set index 2 tag EB and change it to valid. We load the new data here. And for the second one, we need to go to check the. By the way, these are the table. These are the table from the after accessing the memory 1, and these are all the memory address we need to access. So the second one, we need to access the index 0, and the tag is 7A. We go to index set index 0, 7. Okay, unfortunately we don't have 7A, so we need to dump one of them and load it up the new data. And interesting thing is here we have one that is invalid. So we have one line which is invalid. So we have to dump this one and change it to the new one, as can be seen from here. And the third memory address still index 0, the set index 0, and we access 009. We know 09 is valid, right? And we know we do have tag 09 here. Then we access the offset 1, so this bit, the 30. Then we access the return by 0 of line 0. The catch does not change, but line 1 is now least recently used line in set 0. So for the third access, we got a cache hit and we have the information. And the offset is 0, 0. So we need to return the first bit, which is 86. And this is a memory content after the first 3 memory search. And let's move to the third one. Let's move to the fourth one. Index number 2. Let's go to number 2. And tag is 1F. Okay, we don't have 1F, but we do have one line that is invalid. So we need to dump this one and load up the 1F. And from here you can see we loaded up the 1F. And the next one, the fifth one, we need to access the index 0 and tag information 6, 7. Index 0, we don't have, unfortunately, we don't have 6, 7. Um, but and both line contains valid data, and so we replace the least recent user line, which is the line 1. So we replaced this one. This is a eviction policy that we need to that applied here. We use the least recent used policy. So that's why when two blocks are both valid, then we evict the one that is least recent used. And we got the new data here. So and on this is the last memory address we need to access, which is index number 7 and tag number 67. And let's go check the index 7. Okay, we do have 67 tag and it also is valid. Okay, we find our target and offset is 0. Then we return FC. 0 means no offset, right? So the catch set 7 does not contain a line with tag 67, and only line 1 contains valid data. So we replace line 0 with new data. Oh, I'm sorry. I need to use this table because this table was from was after the fifth search. So over here you can see line 7 we don't have 6, 7, but we do have one that is invalid. So we dump the information here and then we load it up. We load it up the the tag 6, 7, and you can see the new one being loaded. Yeah, sorry, this is a result table. The table on the right hand side was a like recent one. The recent so we can use this table to find out the information. This is the most recent one, and this is the one after the search. So that is all for the tutorial 6. And if you have more questions, just leave a comment or email me or send a message on the Piazza or directly send a message on the Canvas as well. So yeah, have a good day. Thank you for listening. Bye bye.